Hello everyone, I'm Alejandro Cabrera, CEO and co-founder of Green Eagle Solutions. First of all, I would like to thank New Energy Update for letting me share with you this presentation remotely. Since we're based in a location with some affected by coronavirus, we decided not to travel this time. Today, I'm going to introduce you to what we believe will be the future of control centers, and we'll share with you some relevant results of what we have called Smart Energy Control Centers, or simply SEC. 3 years ago, we received a call from a customer that we had been working with for over 3 years. He said, Alejandro, we're going to terminate our contract with our manufacturer and I'm looking for alternatives to operate our plant. Could you help us? Most of you probably know Green Eagle Solutions as a software company. We have developed our own proprietary technology called Compact SCADA that is connected to over 300 plants. Compact SCADA is a technology that is behind dispatching centers for companies such as Vestas and Innogy in Spain. But even though our technology was used to monitor and control wind farms and solar plants, up until that time, in 2017, we had never operated them by ourselves. At that time, I was very intrigued to get a better understanding of the protocols and procedures that are required to operate wind turbines from a control center. So we told ourselves, we have been working with this client for over 3 years. We know their assets. We have IT support technicians available 24/7 to provide support service to their OEM SCADAs. And finally, we have the software that is required to monitor and operate these plants. The only piece that we were missing was the actual operations protocols, which we then received from our client. And we realized how simple it was. Basically, the protocol was a list with around 50 rules like the following. What you can see in this table is a protocol of how to operate the turbines based on 2 specific scenarios that I use as an example. Turbine fault by overspeeds or by vibration errors. When a turbine is on overspeed PLC error, we were told to wait for 5 minutes and then send a reset command to the turbine, and if this reset was not successful, we would try up to 5 times, waiting an hour in between each attempt. In the second case of excessive vibration, it was 10 minutes before acting and 30 minutes in between resets. To be honest, it was surprising for me to realize how simple most of these scenarios were. I asked them what they do when a turbine is in faulty state and the protocol doesn't allow them to send a reset command. They said, in this case, you just need to notify the field technician so he can check it out as soon as possible. This notification was, at that time, normally based on a phone call. This customer was a medium-sized independent power producer, and I wanted to know if this protocol was something rare or that most of the protocols that run from control rooms follow a similar approach. After asking a few of other customers, among which we can find manufacturers, bigger independent power producers, and other operators, we confirmed that the structure is similar across control centers, even though the protocol itself, of course, changes based on the technologies and wind turbines models that are being operated. From a traditional control room, every wind turbine incident is managed with careful human analysis, and that requires time. And some of our customers have realized that the response time of these control centers is reaching an average of 20 to 30 minutes. As we're going to see in a minute, this model impacts the amount of production that is generated, but also, and even more importantly, the lifespan of our assets. Additionally, decarbonization and energy transition programs are 2 challenges facing the energy sector. And while these programs encourage a rapid growth of renewable energy, companies struggle to adapt from a centralized power grid to a distributed energy network. This means that the amount of turbines and other elements that are being operated from control rooms is increasing year by year as we move from a centralized energy production to a distributed energy network. Coming back to our customer's request, I was totally thrilled to provide this service. But personally, I have an IT background, and software is what we do. So I could not accept these repetitive tasks to be done manually. From an IT point of view, traditional control centers may be seen as manual phone switchboards of the past century. And we can observe some similarities in the way they operate. As you know, this model eventually became fully automated and made it possible to change the whole industry to what we know today. With this idea in mind, we created our Smart Energy Control Center back in 2017. We believe Smart Energy Control Centers, or SEC, are the natural evolution of traditional control rooms. At the first stage, we provide the exact same service that a traditional control room would provide, with available operators 24/7 from our control room. But by integrating artificial intelligence assisted tools, we automate most of the actions, and now we can provide with the following main two advantages. First of all, strict compliance with the specified operations protocols. And second, immediate time response, regardless of the size of our fleets that are being operated. I'm here today to share with you some of the results we have experienced from this first stage and open the door for the second stage and the next steps of these kinds of operations. The charts I will be sharing now are the results of analyzing the performance of our SEC after operating 6 wind farms in Spain for over 2 years. The wind farms include different technologies: MADE AE52, Gamesa G47, Ecotecnia E74, and Nordex N43 and N62. And here is an example of 2 of them. When analyzing SEC's performance, the first thing we look at is the raw number of errors, bars in blue. The number of remote resets automatically sent from our SEC are represented by the bars in orange, which are obviously not always successful due to turbine technical issues. However, the bars in green represent successful resets, which we calculated to be between 70 and 80% out of all resets performed. Finally, these results show the correct functioning of our technology and yields to an average of up to 0.6% increase in the wind farm's energy production, represented by the yellow line. When plotting the yellow line, which represent the percentage gain in production thanks to SEC and the automation of resets, we see a logical relationship between the number of errors and successful resets. We also notice that peak performance occurs during winter and spring, which are the months commonly identified with high wind speeds. This led us to analyze what exactly happened during these periods of high wind speeds and which type of resets were happening more often. The next graph shows the results of this study. Here, we can see the gain in production in full load hours, represented by the green bars. The blue line represents the capacity factor of the wind turbines at the moment of resets. The capacity factor related to all these kinds of resets resulted in an average of 40 to 50% yearly. But what happens when we only look at the most common errors, which are vibrations and overspeed errors? These are represented by the lines in orange and yellow, and as you can see, they are almost always above the blue line. So the capacity factor related to these 2 errors is higher than the rest. Actually, they represent around 70 to 80% average capacity factor, and again, peak performance is found around winter and spring months. It is important to say that these 2 errors combined also represent 70% out of all errors experienced by these turbines. This opens the door to a deeper analysis, but most importantly, a useful analysis that considers the most relevant events in the operations of wind farms in order to improve operational strategies. Let's zoom in for a second. In this graph, we can see the number of successful resets in gray versus wind speed and the turbine's power curve. Here, it is easy to get a sense of the distribution of resets through the turbine's power curve. And even though it is distributed all along the curve, look at what happens when we plot just the resets related to overspeed and vibration errors. Now, we see that these 2 types of resets happen almost always when the turbine should be performing at its best. Therefore, we can now ask ourselves, is it reasonable to always reset these errors regardless of other conditions? Should we reset them evenly, whether it is summer or winter, without defining a wind condition threshold? Should we keep resetting them when wind speed is as low as here at the bottom left corner of the graph? Should we prioritize the turbine's health and lifetime when we reset at very high wind speeds, knowing that it is when they suffer the most? And what happened to those wind turbines with health we know are compromised already? What if we took into account market price at the same time of these scenarios to decide whether we should reset or not? All these questions target a common goal: defining the optimal operational strategy for each scenario and affected units, considering all possibilities and previous performance. This is what we achieve operating from a Smart Energy Control Center. Why? Because after making a decision, you are confident it will be executed automatically, regardless of the operator's availability. Thanks to this new paradigm of operations, We are transitioning from a linear workflow in which we follow the same rules throughout the lifespan of our assets to a circular one in which we define a strategy, implement it, execute it automatically, and analyze the results over time. Actually, now I would like for each of you to consider the potential improvement considering your own portfolios. What is the average time response of your control room? In our analysis, we consider 10 minutes to calculate potential gain in production. How exposed are your assets to this response time? In our case, we operate these turbines automatically only 16 out of the 24 hours of the day, plus weekends and holidays, basically when there are no field technicians on site. And finally, what is the average full load hours of your portfolio? The higher this number is, the more benefits you experience. For example, we showed wind farms that have 2200s and 2300s full load hours a year, and we have increased productivity up to 0.6%. As I mentioned before, this analysis was made after operating 6 wind farms with SEC and automating the reset protocol that they were following at that time without modifying any of its rules. Therefore, the gain in production shown in this analysis is solely due to the automation of the protocol and not its change. However, we believe that with a circular workflow, where a deeper analysis is performed to then modify the protocol regarding the most relevant errors, has the potential to considerably increase production gains and reduce maintenance costs. But not only that, we are on the verge of full digitalization of the renewable energy industry. But once every turbine has become a data center and have access to the information of all of its components, temperature, vibration, material wear out, external weather conditions, lining probabilities, estimated turbine health state, and all of this in real time, what we must think is how we will manage this data. We propose an automated operations scenario where control systems are data reactive and where operators and owners have the possibility of optimizing the operations protocol as their assets evolve and constantly give information about the real performance. Renewable assets compete in the energy market freely, and focusing on their operation has become critical to the potential financial performance of each project. This is why we believe SEC can not only increase assets productivity, but at the same level of criticality, it can help in the decision-making processes that must determine how an asset is monetized. With SEC, your operations protocol will take into account lifetime extension strategies down to an individual turbine level, spot market price, so that turbines are never working when electricity price is below your maintenance costs. Environmental curtailment optimization, which are becoming more and more important. Noise and flickering optimization, to comply with any state's legal restrictions. And many more variables that are nowadays becoming critical in the operation of renewable energy assets. Thank you everyone for listening. If you are interested in learning more about what SEC can do for your assets portfolio, please do not hesitate in contact me. As I mentioned before, I'm confident this will be the future of renewables operations, but the technology is available today.